If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started.
This case study is about Airbnb. This dataset has been obtained from Kaggle, and it's an open dataset which is relative to New York City Airbnb. As you all must be knowing, Airbnb is an online marketplace and hospitality service that allows people to rent or lease short-term lodging accommodations. We'll be exploring this data and we'll be trying to apply the boosting algorithms to solve this problem. This is a regression type problem which involves predicting the price. So can there be a model put in place? Depending on certain attributes, we can predict what's the appropriate price for an Airbnb listing. Let's get started. All right, so we are at Google Colaboratory and I've already pointed to the data source. We begin by importing the basic libraries that pretty much we need all the time. And now we are reading the dataset using Pandas read CSV. Let's check the shape of the data frame. So this dataset has about 48,895 rows and 16 columns. Let's quickly check the first few observations. So we seem to have an ID column, which essentially identifies the listing. Then we have a name of the property. Then we have a host ID. Then we have a host name, neighborhood group, neighborhood, latitude, longitude, room type, whether it's a private room, entire home, apartment. Then we have the price, and this is the column that we're trying to predict. Then we have the minimum nights that's given. And we have the number of reviews, how many reviews are available for that property. When was the last review received? Reviews per month. So this is the calculation, taking the number of reviews, dividing by the number of months for which the property has been listed. And then we have calculated host listing count, which is the count of listings, and the availability 365, for how many days in a year the property was listed or made available to the guest. So this is pretty much about the features, and now let's start checking the basics. So while we kind of get an idea about the data types when we glance through this, but it'll be nice if we could see properly what the data types are. So we seem to have a mix of numerical and categorical features. And if we look at the numerical features quickly, host ID is a number. That doesn't make sense. It's a nominal variable, so it's fair. We can leave it the way it is. Latitude, longitudes are floats. That's again acceptable. Price is an int. Minimum nights is an int. Number of reviews is an int. Reviews per month is a float because that's a ratio. And then we have the host listings count and availability 365. The numerical variables are appropriate. Let's quickly glance through the object variables. Is there any numerical variable that's being read as an object? So if we glance through it, name should be an object, host name should be an object, neighborhood group and neighborhood should be objects. Room type, again, is a categorical variable, should be an object. And last review is, again, a date element in this case, which it reads as an object. If we want, we can convert it to a date time format, but as of now, that's totally fine. So all the data types seem to be appropriate. Now, this is very important to understand right from the get-go that the data types have been identified properly. Because based on the data type, we will choose different types of analysis of each feature, and we'll give appropriate treatment wherever needed. So it's important to get a clarity on the data type. Now let's move ahead and quickly check for the duplicate records in our data. And thankfully, we already have a listing ID. Whenever a listing ID or a unique identifier is available, we will always check duplicates only on that using the subset parameter. Let's just run this, df.duplicated. We don't seem to have any duplicate record in the data. Now let's drop some of the columns that we believe would be making sense while predicting the outcome, or that's the price. Let's see. So ID, we know we don't need that because it is only to identify each record and we don't have duplicate records, so we can drop it. Host ID, again, is a nominal variable. Doesn't make sense as a number. We don't want to interpret it numerically. So name of the property, again, is not going to make a lot of sense when it comes to the pricing of the property. We are not talking about select few hotels or budget hotels. We are talking about Airbnb listings, right? So people would write something about their property. The name doesn't make sense here. Host name, it could be John, it could be Mary, it could be anybody, but that doesn't matter. There could be multiple names which are repeated as well, but name of the host wouldn't determine the pricing of the property. Latitude, longitude. Now, these are identified as numbers, in fact, floats in our data set, but would we be able to give a numerical importance to a place based on latitude and longitude? The answer is no. The best would be a representation in terms of the categories. But as a number, those latitude, longitude values would not really make a lot of sense because they will bring a sense of false order. So let's drop these columns. all at once. And now we move on to check for the presence of missing values. So we are first checking in the overall data if we have missing values by doing isNull.sum and another.sum to get the total missing value count in the data frame. It says 20,104 missing values are present. Now, since we have missing values in the data, it makes sense to break it by the columns and see column-wise missing value count. So there are only two features which seem to have missing values. First is last review, which is nothing but a date column. And second is the reviews per month. Now, this number exactly matches. Could this be a coincidence? Let's at least deep dive to understand what's the pattern here. So if we select three columns, number of reviews, last review, and reviews per month, and sample 10 random observations out of it, let's see what we get. So if you see, number of reviews is the count of reviews, last review is the date, and reviews per month is the number of reviews divided by the number of months for which the property has been listed, I believe. So do you observe when do we have bands here in these two columns? When the number of reviews itself is 0. So when there is no review, could be a new property, just got listed and they don't have a review to begin with. There can't be a last review date in that case because the property has just been listed. And of course, the reviews per month in this case should be 0. Why? Because if the number of reviews are 0 and you divide it by any number of months, that will give 0. So one thing that's very clear is that there is no point trying to impute the last review column here or guessing the date when there's not been a review. Why would you do that? Second is, reviews per month as a missing value doesn't make sense because we seem to have obtained it like a float properly. If the numerator is 0, anything that comes in the denominator would still make it 0. So let's just change this to 0. We will treat all the missing values in reviews per month with 0, and we'll drop the last review column because taking an average of dates doesn't make sense. So what we're doing is we are dropping the last review column, and then we'll be left with one less column. Once again, for the missing values, now that we have just one feature which has missing data, which is the reviews per month, let's just impute it simply with a value 0. We are not taking a mean and putting it there because the property has not received a survey till now. So we input it as 0, as simple as that. Now let's move on to, once again, checking the missing values if those have actually been treated, and should be the case. So we see there is no missing value in the data. Now we actually can check the columns and we have a mix of features, if you remember. So let's try to segregate the features in terms of numerics and categorical features. To begin with, we will use pandas select d types to filter out the numerical feature list. So when we do df.select d types, this is the data frame. When we do dot columns on it, that returns a list which contains the names of the numeric features in this case. And let's check how many numeric features we have. So we have 6 numeric features. Now for numeric features, we might quickly glance through if we have outliers present in the data, just to visualize and get an idea about it. So we are doing our common subplot thing. We're taking a for loop, iterating over the range of numerical features, and using the pandas subplot, we are creating 2 rows and 3 columns, kind of a grid, where all the features will be plotted. So let's just run this, and we see that apart from the availability column, which has an obvious range of 0 to 365 kind of values, all the other features have outliers. In fact, even the target column has outliers. We can check the descriptive statistics of the target column to look at it closely. And this is a continuous numerical variable, ranges from 0 to $10,000. Now, 0 is a little surprising, but we'll check how many such observations we have. And it's as expensive as $10,000. Looks like this is a pretty skewed column because your 75th percentile is at 175. So what we're doing here is we are quickly checking how many properties are listed for a price 0. It says 11. So there might be an adjustment or a refund in a particular case. That's why the price seems to be 0. But in any case, these 11 observations would not make much of a difference when our base that we are working on is about 48,000 records. So we can ignore this for the time being. If we want, we can always modify this value with a central tendency or something else. But in this case, the quantum is so small that we can simply ignore it. So I'm skipping the next few lines and moving on to checking the descriptive stats of the entire data, because we found a peculiarity with respect to price. I'm just wondering if there could be other places as well. So minimum nights could be 1 to maybe 1,250, could be a total, and maybe a host has multiple properties. That's again possible. Then we have the number of reviews, 0 to 629. Okay, then we have the reviews per month. That's again a feasible value. Post listings count, that's again a feasible value, 1 to 327. and availability is from 0 to 365. So more or less all the other features, the minimum maximum values seem to be okay, apart from the price column where the minimum value was 0, but the observations were so limited that we chose to ignore. Now let's take the numerical features and check the correlations between them. So note in earlier version of Pandas, this was automatically selecting the numerical columns when you pass any data frame. But of late, it has started giving a warning for not specifically choosing the numerical features, and it'll soon be deprecated. So it's a better idea to choose the numerical features selectively. This is the same numerical column list that we created using select D type some time back. We are creating a heat map where we are passing the correlation matrix and just trying to visualize if the features have correlations. So we don't seem to have a strong correlation here, which is to the north of 0.8 in either direction. We seem to have okay-ish kind of correlation, so we are fine with this. Moreover, for the decision tree-based models, and even for boosting algorithms, if they're using decision trees as inputs, neither the outliers matter nor the correlations between the dependent variables matter. So we don't have to worry too much about it. We just class through it. Now let's similarly select the list of categorical features and examine them closely. So we had 6 numerical features and we seem to have now 3 categorical features. And if we quickly want to check how many unique levels are there for each categorical feature, because categorical features are always encoded before they are passed on to a model. So for neighborhood group, we have only 5 categories. For room type, we have only 3 categories. For neighborhood, however, we seem to have 221 categories. So this is something which is a bit problematic. For the other columns, we may not necessarily have a sense of order. If we have any specific intelligence, we may apply that. But let's say for neighborhood group and for the room type, depends on what the location of the property. So a single room in a luxurious property could be more expensive than an entire apartment in a not so good locality. So we can't really give an order just based on the room type. These columns, room type and neighborhood group, could be easily one-hot encoded because we don't have a sense of order. But neighborhood group and neighborhood, we may want to check, just like some time back we checked between the number of reviews, last review, and the reviews per month. We may want to check these 2 columns together if they have some correspondence. And we are just filtering these 2 columns selectively and randomly sampling 10 records out of the data. So we seem to have more granularity covered in the neighborhood. Neighborhood group, as the name suggests, would capture a broader category. Neighborhood in itself would capture more options. For example, within Brooklyn, you see there are multiple options that are listed. Within Manhattan, you have East Village and Hell's Kitchen. So you seem to have more choices in neighborhood, which you don't have with neighborhood group. We'll see what we want to do with this. But at this stage, let's do a split on the data. So far, we've not made major changes to our data, except for fixing a few columns like reviews per month and dropping the columns that we didn't need. We just examined the other columns, but we have not modified any value anywhere apart from the missing values. Now let's go about splitting the data and split the data into X and Y and then do a train test split. So we are keeping the 30% portion reserved as test and remaining as train. Now in this case, we would first want to proceed with the encoding for the categorical variables. Now there is one variable which has too many categories. This is something we have discussed in our theory videos, that when a variable has too many categories, we can always perform a target encoding. Now, at the time when I'm creating this video, the target encoder in scikit-learn isn't working that great. So we are using the target encoder from category encoders. It needs to know which column you want to do encoding for. So if we don't mention anything here, it will choose all the categorical columns. But we know that there are 2 categorical columns which are already sorted. We have minimal levels there. We don't want to treat them. Neighborhood column, which had about 200 plus categories, is what we want to treat. So let's just run this. We are just calling the target encoder, instantiating it, and doing a fit transform on train and just the transform on test. This is a supervised method. That's why at the stage of learning or fitting, it needs the target column as well. The name itself is target encoder. It would need the target column always. And then on the test, we are simply doing a transform. So once we've done that, this would have taken care of the neighborhood column. For the remaining 2 columns, which are neighborhood group and room type, we are doing a get dummies or one-hot encoding in this case. We are doing it separately for train and test. Notice this does not have a fit transform, so we can directly apply it on train and test. Now, let's quickly glance through the encoded data's head. And what we see is that neighborhood column, which had 200 plus categories, has got a numerical encoding. All the other features seem to be numerical as well, where we see the neighborhood groups as one hot encoded, and so is the case with the room type at the end here. So our data is all numerical now, and we can start fitting different models one after the other. Let's start with a decision tree, because this would mostly be acting as a base estimator for most of the boosting algorithms. So let's at least do a decision tree. Now, one new step that you see here is a randomized search CV. So far, in most of the examples, we have used grid search CV. So there's a fundamental difference between these two. Grid search requires us to pass a grid of values where it'll check every possible combination that's available in the grid. And that is very time consuming. That makes the process very, very slow. It's going to do it 100%, but it's very time consuming. Now, randomized search is somewhat smarter in that sense. It doesn't ask for specific values. It asks for a distribution or a range of values that you want to give. So it wouldn't try every possible combination. It would randomly select some combinations from the overall combinations possible and gives you the result. So this is somewhat faster. And in order to give the inputs for various hyperparameters like distributions, we are also calling the randint and uniform distributions from the SciPy library. Let me just run this, and then I can show you how this works. So we are instantiating a decision tree regressor at this stage without any hyperparameter mentioned, but we are creating a parameter distribution. So this is called a parameter distribution. The name of the hyperparameter in randomized search itself is parameter distribution. So we're just naming it like that here. Then we are creating a dictionary, max depth. Notice we used to pass a list of values like 3, 5, 7, 9. Here we are saying we want to take a random integer from 3 to 10, 3 inclusive and 10 not inclusive. Min sample split, again, we've given a range of values. And min sample leaf, again, we've given a range of values. So it will randomly sample from all possible combinations that these values can attain. But how many samples? That's something which is controlled by an iter here. So if we take a greater value for it, it'll explore more hyperparameter combinations, but we've limited it to 20 here, which means we are saying from this hyperparameter space where you have a range of values that these hyperparameters can attain, choose 20 combinations. And rest everything is same as the grid search CV. So we are again calling the model, we are calling the parameter that we've defined above, we are doing the cross-validation. And since this is a regression problem, we are mentioning the R-square as the scoring parameter. Please note, randomized search, because it will be searching the space randomly, if you do not mention a random state, might not give you the same results. So this again needs another parameter, which is random state. We have mentioned a value there. We're calling it DD search. Finally, we do a fit, just like we did in case of grid search, of the encoded train data and the Y train, and then we find the best estimator out of it. If we run this could take some time because we are trying to search a space, but it'll definitely take lesser time compared to grid search CV. So now the randomized search has finished, and we can move on to predicting using the best decision tree model that has found. So we do separate predictions for train and test data. Both the places, the encoded data is given as an input. Finally, when we have the predictions available, we can call the R2 score from the scikit-learn library, and we can calculate the R2 score for train and test separate. So let's look at the performance of our decision tree. It doesn't seem to be very encouraging though, because it's only showing 23% R square in training and 6% R square in test. That's really bad. Let's see if we can get it any better. So what we're doing is we are next calling the AdaBoost regressor. Now, you know, AdaBoost is an adaptive boosting technique which uses decision stumps or simple decision trees and then tries to learn from the mistakes and improves them over a period of time. Let's take the decision tree regressor, called the AdaBoost regressor, pass the decision tree as the base estimator, and we are again using a randomized search here. So we are passing a range of values for n estimators. It will be creating multiple trees. AdaBoost creates multiple trees. So we're giving a range of values for those trees. 50 inclusive and 200 not inclusive is the range that we've taken. Learning rate is the weightage assigned to different trees when you create the model. So it's a scaling factor. We have that mentioned over a range here again. We are saying that will be uniformly distributed. Now, if you want to specifically tune any hyperparameter in your base estimator, the way to do that is that you mention the name of the parameter and with double underscores, mention the name of the hyperparameter. Max depth will be applied to this decision tree regressor, which is actually the base estimator. And we are giving it a range of values from 3 to 6, essentially 3, 4, and 5. And this has different types of loss functions. So when you say linear loss, it's the absolute value of the difference between actual and predicted values. When you say squared loss, it's magnifying it further and considering it as a bigger loss. So we've given a kind of grid for that, and then we simply call the randomized search CV. We call the AdaBoost model. This is the AdaBoost regressor, the parameter distribution that we have mentioned here, and iters. We'll take 20 combinations of these. We'll do 5-fold cross-validation. This is getting scored on the R-square value and the random state for reproducibility of the results. We do a fit, and then we finally get the best estimator using this attribute. Let's run this. And this step might take time. Even though we've used randomized search CV, it will still take time because this is a complex algorithm. But it will definitely be faster compared to a grid search CV. If you would have tried in this case, it would have taken forever to finish. Let's just let it finish and then we'll see the results. All right, so finally it is finished, and let's see when we do the predictions using the best AdaBoost model, what's the kind of result that we get. So we're generating the predictions for both train and test set, and then finally obtaining the R-square value. Okay, so this is somewhat disappointing. First of all, the R-square for training set is only 13.79%, and for test, the R-square actually is negative. Now, I kind of leave this open for you for the time being to figure out how can the R-square value be negative? Because it's mostly seen to be positive and people say it's always between 0 to 1. But in this case, we seem to be getting it as negative. Is that even possible? And maybe we will discuss that separately. Now let's move on to the gradient boosting regressor, and we are initiating the gradient boosting regressor from scikit-learn ensemble. And then we are passing a hyperparameter distribution for this as well, where we are mentioning the number of estimators. Again, gradient boosting would require multiple trees. So we're passing a range of trees. It requires a learning rate, which is nothing but a scaling or weightage given to different trees. And then we have max step for the trees. We have the min sample split, min sample leaf, exactly the same way as you know them from trees is the interpretation of these here. It's just that these would be applied to multiple trees. Now, subsample is another option which helps us avoid overfitting. This would only consider a certain portion of the overall data while training, not the overall data. So we can give a high value like a 0.8, 0.9. That's another option that we are trying. And max features. So when we create multiple trees, even for the trees, we will be taking a subset of features in certain cases. This is exactly the same way as you know it from random forest, right? And then we are passing all this distribution to the parameter distributions inside the randomized search CV. And all the other parameters are as explained. The only difference is that the model this time is the gradient boosting model. We are fitting, and then we are doing a best estimator check on that. This again might take some more time, but like I said, it'll still be faster compared to grid search CV. So let's see. Okay, so finally the gradient boosting has finished learning, and then we are going to use this model to generate the predictions for train and test set separately. Again, the standard way we are calculating the R-square value for train and test set. Again, so this seems to have a somewhat better training score, which is 38%, but the test score is only 16%. This again doesn't seem to be a great model. We may say this is better than what we've been able to see so far, but overall not a great model, and it's again not stable. Now finally, we are calling the XGBoost regressor. Again, XGBoost regressor is not available within scikit-learn library, so we are calling it from a separate library called XGBoost. And then this has a separate set of parameters. So whatever arrangements we've mostly seen, like the parameter grid and all, was primarily for scikit-learn based model. For XGBoost library, there is a different way to mention the hyperparameters, and we are going to go over this list. So this eta here essentially represents the learning rate. It has the same interpretation. Max depth has the same interpretation that you already know. The min child weight here is the minimum sum of instance weight needed in a child. It is essentially used to control overfitting by higher values, making the algorithm more conservative. Then we have gamma, which specifies the minimum loss reduction required to make a further partition on a leaf node of the tree. Then we have subsample, which has the same interpretation as we discussed some time back. Then it has column sample by tree, which is essentially the same hyperparameter like the max features. And then we have n estimators, which again has a similar interpretation. So a lot of these are same, except for a few places where the names are somewhat different. And the way to pass this is by using these two asterisks and then writing the params dictionary here. And then we can just do a fit on this one. So it is finished running. Let's use this model to generate the predictions. XGBoost will be relatively much faster compared to the adaptive boosting and gradient boosting. That's why it's called extreme gradient boosting. You'll find that when you run this code yourself. Now, let's predict the R-square value for the train and test set exactly the same way. And even the XGBoost is not doing that great. It seems to be doing relatively better on the train set at least, because we've not seen a value so far on this data which has crossed 40%. This at least is about 42%, but on the test, it's only 16%. So just to summarize everything, putting them all together, we're creating a data frame which captures the names of these models and their train and test performances as a dictionary, lists being passed as values for these keys. This would lead us to a data frame, and let's just quickly do a comparison of the 4 models that we have seen so far. The decision tree was not that good, 23% in training and 6% on test. AdaBoost was, in fact, the worst because training performance is the lowest and test performance is actually negative R-square, which is shocking. Gradient boosting was somewhat better, again, not great because it's not a stable model. And extreme gradient boosting, if you see, relatively the best, but again, not a great model overall here. So what has gone wrong here? We've done everything the way we were supposed to do. Still, we don't seem to be getting very good results. Now, there's a slight twist, which will not give us great results, but will give us something that will be interesting to observe. Let me take you a few codes up and show you how we can bring that change here. So there were a few lines of code which were purposefully commented, and I'll tell you what's happening here. So if you see the price column had outliers. Now we know that decision trees and boosting algorithms are not sensitive to outliers. But what is it set for? Is it set for independent variables or it's true even for dependent variables? The fact is that when we generally talk about an algorithm not being sensitive to outliers, it's said with respect to the independent variables. There are algorithms which are sensitive to outliers when they're found in the dependent variable. In this case, if we take the 95th percentile of the price column and choose that value, because if you see, the 75th percentile of the price column was only $175, but the maximum value was $10,000. So let's see what this value is at 95th percentile. In fact, you'll see that value is 355. We will see how many records we had to begin with and how many records will be left with if we filter out all the values which are greater than 355. Let's just run this. So we had 48,895 records. If we drop the values which comprise of the top 5%, we'll still be left with 26,444 rows, which is a decent amount of data. But we'll be more realistic with respect to a target column, which will range from 0 to anything up to 355, but not inclusive of 355. We are applying the simple filter on the data. And now what I'm going to do is I'm not going to repeat that entire code for you, but I'll quickly refresh this code. And after this finishes running, we will compare the performance of different models. So we are once again running the decision tree, and let's just see what the performance for the decision tree that we get. So this was about 24% and this was 6%. You see, this has become 56% and 53%. By doing what? Just discarding the 5% of our data, which was full of outliers. And it's now running for the adaptive boosting regressor. Let's see what its performance is like. But this definitely seems better compared to what we've seen so far. Even the extreme gradient boosting technique was not able to give us 56% performance on training and 53% performance on test. It was able to give about 42% on training and 16% on test. It's still running for adaptive boosting. The only change is that we have applied a filter on the Y variable, and not to an extreme extent. We've just applied it to capture the data which falls within the 95th percentile. So finally, adaptive boosting regressor has finished learning, and if we quickly check the performance output, even this seems better. At least it's not giving us the R-square per test, which is negative 20%. It's relatively a lot better compared to the previous version, 51% on training and 49% on test. If you see, the performance results are not that great even now, but when we say it's great or not great, what are we comparing it against? If you actually have a model which gives you better results than these, then you can say this is not a good model. But if this is the best result that you have, then that's the best option that you have right now. Till date, for a lot of models where we do create risk modeling, the R-square value that's benchmarked is about 30 or 35%. So we should not always be expecting a 90% outcome. It totally depends on what's the best result that we can get with a given data. And this definitely is a lot better compared to the previous version. So the takeaway so far is that the outliers in the target column actually do affect the model performance, even for decision trees and boosting algorithms. Now we move on to the gradient boosting regressor, and this again is going to take some time, but we'll just patiently wait for it to finish so that we can compare the pre and post performance. Finally, the gradient boosting regressor is also finished learning, and we can quickly check the output. So this is 59% versus 56%, a lot better compared to the previous version for sure. And now let's check the XGBoost regressor. How does it look like? The XGBoost regressor again has given about a 59% and 56%. If we once again create the same comparison grid that we created earlier, here is how it looks like. Definitely many-fold better compared to what we had earlier. The performance of adaptive boosting model is somewhat lagging compared to the other models. Though it's not far behind, but the best performance on test is only 49%. But the best performance on tests that we have for other models is going up to 56%. So there's clearly a difference of about 7% in performance there. Decision tree is not that lagging behind. Being a simple model, it's able to give about 53% on the test data. And training as well, it's giving about 56%, so that's decent. Strictly speaking, gradient boosting and extreme gradient boosting seem to be the best models here. And there's not much of a difference in their performance. It's a minuscule difference at the second or third decimal places that you see in both training and test. So both these models are relatively better in this case. So this was an example of applying boosting, that too to solve a regression problem based on the Airbnb data. Hope you had some interesting learnings out of this case study, including the data preparation and the best piece, which was related to the influence of outliers in the target column. Notice we did not really replace the outliers or treat the outliers here. We simply chose to work with the majority of the data, which was not affected by the extreme outlier values for the target column.